cloud. Però nel cloud di chi? Nel cloud mio?
C'è così, ma si va così.
Sì?
Non ha, si disattiva l'audio poi. E il video, scusa.
Allora, so again, can you hear me?
Yes.
Can you see my
Yes, we
screen?
can.
Yes, we
Yes.
can see the screen.
Okay, nice. Then we can start the last. Okay, it was this one. Okay, yes. The last lesson of this short course on ultrasonic wave propagation in classical and non-classical continua. Sorry, and today we will discuss kinematics and dynamics of periodic discrete systems endowed with at-distance action and rotational degrees of freedom. The first of these two is basically the second gradient continua, and those ones which have rotational degrees of freedom are the Coursera continua. And we will see how waves propagate in this kind of media and how to operate a discrete to continuum transition. We will also present the propagation of bulk waves in this kind of solids of continua as well. I'm not sure exactly what time I'll be finished with that, but if I have time, I put in gray these parts which unfortunately I have not managed to develop for this year. This is going to be for next year. But if I will have time, I will show you some cases, some applications of the models and methods we have discussed in these days. So let's start with the elastodynamics of second gradient media. First of all, I would like you to give a look at this drawing. So what is in practice a second gradient continuum? You have to imagine a chain of 1 degree of freedom oscillators. Each one has a mass, and it is connected not only to the adjacent oscillator as it is in a classical continuum, for instance, the bar, which we discussed, when was that, 2 days ago. But there is also an interaction between particle I+2 and I-2. So you see that the ith oscillator is connected by a spring whose stiffness I have called K2, together with the oscillator I plus 2 and I-2. This is called at a distance action because we've got both a local interaction, which is this one, the one which is expressed by the spring K sub 1, and at a distance interaction, which is expressed by the spring K sub 2. Generally, this interaction is not taken into account, and this K sub 2 is very small. This is why we mostly use classical continua, but this can be not generally true. And if you have actual springs, like in this case, you have to take into account that stiffness. Otherwise, the model you are using does not account, is not able to describe exactly the behavior of the system you are analyzing. Now, if you observe the free body diagram, you see that you have the usual inertia force. This is the same. And then you have the interaction between adjacent particles, which is this one, which is exactly the same as we saw 2 days ago. And plus, you've got these other forces which are due by the action of the springs, which depend on the relative displacement between at the distance point. So this depends on K, basically the force is K sub 2, stiffness, times U sub I plus 2 minus the displacement of the oscillator we are studying. Okay, so the difference between the interaction, the local interaction between adjacent particles is this one. We have a couple of additional forces. In this case, the interaction is limited to particles I plus 2 and I minus 2, but in general, you can imagine oscillators that interact with oscillators that are even at a larger distance. It depends on the kind of continuum you are, or on the kind of system you are studying. Using the usual method, if you write down the equations of motion, you obtain an equation which contains also the displacement. This is the balance equation for the ith oscillator, and you can see it contains also the at the distance actions, which are these ones. With the usual method, which we described for the classical continuum, you can imagine to make it continuous. The longitudinal abscissa is x, and if you expand all these terms in a Taylor series expansion up to the 4th order, you obtain this formula, which when you substitute them in this equation of motion, enable you to obtain this equation. Now you can observe what is the difference between the old one. This is the new one, this is the old one. So you've got the second derivative of the displacement field, which you had here. You can see here there is a contribution of it at a distance action also in the classical term. And there is also another term which contains the 4th derivative of the displacement field. And its stiffness, the stiffness which controls this term, derives both from K sub 2, which is the stiffness of the at the distance particles of the spring which connects at the distance particles, and on the stiffness of the spring which connects adjacent particles. Now this difference is that this one counts much less than this one, because you see that this one is 1/12 and this is 4/3. So this one is much more important, but obviously it depends also on the value. And obviously, if you go to the limit for K2 equal to 0, you are missing this term, and then you've got here a to the 4. If a is very small, this term is negligible with respect to this other term, and you return to the differential equation that you had obtained before in the case of just local interaction. Okay, the equation we wrote before, this one, represents, in fact, the balance between two internal forces. One is the usual, I'm not sure there is a way to make this object a little bit more visible. Maybe I can use this one. Yes, maybe. I'll try. Try to use this. No. Just a minute. Sorry, because I would like to have a red dot here. Do you know how I can have a pointer here, guys? Scusate, sapete come posso trasformarlo in un puntatore? No? Scan. No, però...
Adesso forse provi a fare tasto destro, dovrebbe esserci... No.
C'è il puntatore qua, ok,
sì,
sì, questo, certo, io lo vedo un po' male, un po' bruttino, vabbè, però
Qui si vede abbastanza bene.
ma loro vedono online you see, I guess, the small picture.
Yes, we see the small picture.
Mm.
But you can share the... You can share the screen and you share it on the screen.
Mm. How can I do?
Yes. No. Now they should have the...
Is it better right now?
Yes, yes, it is.
Okay, so you can see the whole picture. Okay, thank you. No, not now. Wow. I was trying to. Okay. Yes. Okay.
Sorry, from home we can't see the share screen anymore.
You can't see it?
We can't see the shared screen anymore. Non vediamo lo schermo condiviso.
Sì. Let me try. Yeah, but I was trying to use the pointer, and the point is that they don't see very well the screen. Can I do something?
Use the mouse.
Yeah, it's not really nice.
They cannot see that screen in the camera.
No, the point is that the people who are online can just see a small screen, a small version of the screen. They don't see this one.
Perché vedono il secondo schermo.
Yes.
Lo mettere
It is, but it,
Yes.
Quindi
it's
esca dalla
visible
presentazione.
enough, I think.
Ok.
Sì, scusate, in questo momento non è proprio condiviso lo schermo.
Sì, un attimo.
Ok,
Ma io
niente,
no...
scusate.
Sì, ma questo è quello che abbiamo fatto ieri, ma io non ho il puntatore qui. Lo faccio.
Forse ce l'ha, provo a vedere. No, non ce l'ha.
No.
Però riescono così a vedere il mouse.
Vabbè. Sorry, I'm sharing my screen again. Condividi. I can use this one, I guess. Maybe I can draw. Yeah, I use this. Okay, so I was saying that this equation represents the balance between two internal forces. This first one, is the normal action. And another one, which is this one, is what you see generally called in a second gradient capital T. Now, capital T is a hyperstress. It is what is called hyperstress, this one. And if you check out this relationship from a dimensional point of view, you can see that the hyperstress is in practice a couple of forces per unit length, acting in this case. Then I have made some drawing to show you what it's like in 3 dimensions, in this case, acting along the x direction. So it is actually a couple of forces in the one-dimensional case with 0 couple. It's a couple of forces, but acting on the same line. Therefore, their contribution to the longitudinal balance is given by the increment of this couple of forces divided by the space dx. So dt over dx is actually a force. Now, the constitutive relationship is this one, which is exactly that one, where, as you see, the deformation parameter is this one, and it is nothing but the derivative, the second derivative of the displacement field. No, this is a bit too much. No, this is too much. No, look at. Can I clean it? Oops. How can I clean it? Same tool, annota. Cancella. Ah, okay, nice. Okay, feel better. Okay, so right now we have seen the transition between a system of discrete particles and a second gradient continuum. Is it clear? And now I will enter to what is presented in books, in articles, as a second gradient continuum. And you see that a second gradient continuum is basically a continuum where the displacement of a point is described by 3 components of the displacement. The difference between the classical continuum is that in this case, the strain tensor is the same thing, but you have a second tensor which describes, in this case, something like curvatures, which is a second gradient tensor, and it is this one. The stresses are of 2 kinds. One is the usual Cauchy stress tensor, whose constitutive constants can also be different. I have reported here the case of an isotropic material, and I will give you also some references where there are explained, you can have explained the different constitutive constants and how they relate, and also the values these constants must have in order for the strain energy to be positive definite. And so let's go. So this is the stress tensor, and this other object is a representation of the hyperstress. You see, as I told you before, couple of forces acting at a distance with arms according to the different direction. And its ijk component represents a couple of forces acting along the direction k, the last index, on the plane with normal j, and with a lever arm in the direction I. Okay? And if you if you write down the translation balance, you obtain something like that. You see, on one face of the infinitesimal element, you have the variation of the couples. And on the other face of the element, you've got the variation of the couples, so the second derivative. The second derivative depends on the second derivative of the displacements, so that in the end you come up with an equation of motion in terms of displacements, which contains fourth derivatives of displacements. And this equation has more or less this expression. You've got the divergence of the classical stress plus the divergence of the hyperstress, which you see is the variation of the variation. Why? Because T is a set of couple of forces with lever arm according to the different direction of spaces. Therefore, you've got to derive it twice to obtain quantities that express the unbalance of forces. I have reported here some relationships and also some constitutive relationships for an isotropic hyperstress, which are these ones. And a isotropic second gradient continuum is described by 7 independent constants. You can find some more details into this paper, generalized Hooke's law for isotropic second gradient materials, which I have reported here. Now, let's go back to what we did a couple of days before, because we said we are interested in the wave propagation in these kinds of continua. So what can we do? Exactly the same thing we do in the classical continuum. We pick up a tentative solution, which is this one, and we substitute in the equation of motion. If we do that, after some algebra, you come up with this balance equation, which describes the propagation of plane of harmonic waves with a plane wavefront, which is this one, in second gradient media. And this also enables extraction of the acoustic tensor, which is this one. And this acoustic tensor has a simple spectral decomposition. This is very nice because, as you remember, in Cauchy continuum, the spectral decomposition enables you to conclude that it is quite easy to derive the propagation of waves that act, and especially if it is something exactly like that, you've got just one wave which goes, whose displacements are in the same direction of the normal to the plane of the wavefront, and another wave whose displacements are contained into a plane which is orthogonal to the normal of the wavefront. Exactly the same thing. Now, the part of the solutions that are include displacements normal to the wavefront are those ones, because this I minus n tensor product n it spans the plane orthogonal to the normal to the wavefront, while this one spans exactly the normal. So this one is shear waves. And you see that these are shear waves exactly with the same speed as we get in the Cauchy continuum. But things get more complicated for waves that are longitudinal waves. In fact, to obtain the velocity of these other waves, you've got to solve this equation so that you obtain that the wave number is related to the frequency by this other relationship, where, as you see, the Lamé coefficients appear, as well as this other constitutive constant, which is the sum of these other 5 constitutive constants that describe the the at a distance actions. The interesting thing is here that these are 2 dispersive waves. The minus here just represents the direction of wave propagation, but you see here that you've got also plus or minus. So you've got 2 dispersive waves. One of these waves is complex, because you see here minus plus, and the other one, obviously it also depends on the sign of this term, but this term is generally positive, because this quantity is generally larger than this one, unless for very large frequencies. So you've got one evanescent wave and another a complex wave number, which means wave that propagate but whose amplitude is attenuated while they propagate in space. And in this case, you see here I have reported the normal to the wavefront is this vector here. So this one direction, this one space, this is a space, is n tensor product n a, and this other in red is this the plane spanned by this decomposition I minus n tensor n times a. And here I have reported the wave number, real part and imaginary part, as a function of frequency. So you see shear waves are represented by this red line. This is a constant. It means what? The derivative, if you take the ratio between omega and k, you obtain the velocity, and this is a constant value. In fact, this is the velocity of shear waves. These other couple of waves are exactly this other couple. One is the one with the plus and the other is the one with the minus. The one, the black one is the longitudinal propagating, and the blue one is the longitudinal evanescent. So in this case, depending also on how you set the structural, the constitutive constant, you can obtain real or complex. Anyway, here I got just real and completely imaginary wave number. If you check out the speed as a function of velocity, as a function of frequency, you see that this horizontal line represents shear waves, so constant velocity. These are non-dispersive waves, okay? Shear waves are non-dispersive also in the second gradient continuum, while the black curve represents longitudinal waves. And you see that here, in this case, this is phase velocity. Phase velocity changes as a function of frequency. So longitudinal waves in second gradient continua are dispersive. This is their expression, and the velocity can be obtained just by calculating the ratio between omega and k. K is this one. Now, do you have questions on this first part? Yes, tell me.
Case of media with electromagnetic properties.
Mm-hmm.
Can they be modeled by this second-gradient dipoles?
Electromagnetic properties, I don't know because I haven't worked on that. But if there is at a distance interaction, for sure, a second gradient continuum can be used. Even though, as far as I remember, electromagnetic fields, just fields, but not without an interaction with the solids, so I'm not sure we are talking about the same thing, are just are not second gradient. They are coupled. There is a coupling between the electric and magnetic field, but it's not second gradient as far as I remember. Okay, then let's move on to the elastodynamics of Coursera media. So again, this year I made all these drawings because I think they are useful to better understand what is the meaning, what is the reason why we should study and use in practice these models to describe real engines, real objects. So I tried to imagine a mechanism that is in practice a Coursera continuum. So I have imagined an infinite system of particles that are these disks. I made round particles instead of square particles. These particles can translate longitudinally. In fact, you see I put this small wheel, but they can also rotate. They can rotate according to an axis which is normal to the plane. Okay, so the configuration of a particle of one of these small rigid wheels is described both by its axial displacement and its rotation. Okay. Now we assume that particles just interact with neighboring particles, so that the ith particle just interacts with particle I plus 1 and particle I minus 1. How do they interact? They interact with these springs. They are springs with the same stiffness. I put them to begin with the same stiffness. So if the particle just moves horizontally, the two springs are stretched or elongated, but also, and this is the forces, the reaction forces that act on the particle. You see K half times U sub I plus 1 minus U sub 1. Okay, so this is the part of the reaction force just due to the stretch of the springs. But if the particle rotates, you see that this point moves. And in particular, it moves of a quantity which is r, the radius of the particle, times theta sub 1, the rotation, for small rotations. And this also causes the springs to stretch. So imagine an anti-clockwise rotation of this particle. You've got this particle is stretched, and this spring is stretched, and this other spring is compressed. Therefore, you will have a couple of forces acting on this particle. So you've got to take into account of the action of these actions and not only require translation balance, but also require rotation balance. So this is what I said before. The spring elongates, and this results in a force. Sorry, this is elastic force. This is U, and a couple, which will be this one. So what is the value of inertia in the case of the rotation balance? Let's give it a look. The inertia of an infinitesimal area of the disk opposes that, sorry, an infinitesimal area of the disk opposes to rotation about its center is rho, the density of the disk, time its area, times the area is r dr times d theta times double dot of the displacement, the second derivative of the displacement. But for small rotations, the second derivative of the displacement is, sorry, this is small r times double dot second derivative of the rotation. Therefore, if you calculate the total rotational moment of inertia, you obtain rho pi, fourth power of the radius divided by 2. And this is the J, generally called in equation J times theta, second derivative of theta. You do exactly the same thing we've done before. You write down the balance in terms of when using the constitutive relationship between forces and reaction forces that express reaction forces as a function of displacement and rotations, and you obtain these two balanced equations. You make them continuum, you use Taylor series expansions, and you obtain these two nice equations that are nothing but the equations of motion of a Coursera continuum. Because you've got one equation which concerns displacement and another equation which concerns rotations. The only thing, pay attention to that, is that this time you've got two decoupled equations. One represents axial waves exactly as what we have in a bar, exactly as what we've done for the system of particles interacting locally. Plus, you've got another equation which represents rotational waves. These rotational waves are kind of waves that propagate in space and just involve rotation of the particles, no displacement. These equations were uncoupled, but they might be coupled. When are they coupled? Consider the case when the two springs have a different stiffness. If the two springs have the different stiffness, there is an imbalance between these two forces, and in this case, the equations become coupled.
Sorry. Also the rotation of the area.
Can you repeat your question?
What if the particles also can interact with rotation of the equipment, not just translation?
Yes, this is the case, because you see that, I'm not sure I understood your question, but you see that if now I probably understand. It depends on how the springs are placed, okay? Because here I try to make things very simple and use only translational springs. I'm not using rotational springs, but rotational springs can exist. So in that case, probably in that case, you've got a direct, you can have direct couples deriving just by rotation. And in that case, you don't have any couple if you have just a displacement. Depends on the structure. I invented, kind of tried to imagine this kind of structure to explain in a very simple way what is a Coursera continuum. This is something that also a student at the fourth year of engineering can understand. I like simple things. I try to make things as simple as I can. Okay, so now let's go back to the theory of the Coursera media that you probably have studied with Professor Trovalusci. So what is the difference between the Coursera medium and a classical continuum? The difference is that if you consider a very small area of the continuum and you go to the limit of this area becoming very small, in the Cauchy continuum, you have just tractions acting on this infinitesimal surface of normal n. And there is the assumption that the couples tend to zero, so that they are neglected in the analysis. But in the Coursera continuum, you do not neglect these microcouples. A Coursera continuum has also another characteristic. Not only this this couple is not zero, but also each point of a Coursera continuum is endowed both with displacement and rotational degrees of freedom, so that in a three-dimensional continuum, to fully describe the configuration of a point, you've got to specify both its displacements and its rotation. Now, the thing is, rotations can be represented basically in two ways. You can represent it by a vector. These are rotations about the three coordinate axes, or in matrix form, like that. And the relationship between the rotation matrix and the rotation vector is exactly this one. And we say that the rotation vector is called the axial vector of this matrix. It means that when this matrix acts on a generic vector V, the result is exactly equal to the vector product of the rotation vector and this same vector V. Okay? What is like the balance of forces in a Coursera continuum? This represents the tensions acting on the faces of an infinitesimal solid extracted from the continuum. These are the tractions, and these are the couple stresses. You see that on each face, you've got also three components of the couple stress. If you imagine to write down a rotation balance, you can draw it like that, and you come up with this kind of equation where here you just have the classical stress components, the components of the classical stress tensor. Okay, so I have considered here the case of an isotropic linear elastic Coursera medium, again, to make things simple. And these equations, in the case of the three-dimensional solids, are a total of 6, because you've got 3 equations expressing translational balance plus 3 equations expressing rotational balance. In this case, the stress-strain relationships are these ones, S and M. So S is a sort of, as you see, you've got here 2 mu and lambda, multiplying the trace of gamma. This is a sort, this is what in a Coursera medium corresponds to the Cauchy stress. This is not exactly the same. Why? Because the constitutive relationship is not between elastic constants and the symmetric part of the gradient of U. You see that this is not the symmetric part of the gradient of U, which will be calculated as 1/2 of the gradient of U plus the transpose of the gradient of U. So this is something slightly different. Is the gradient of U minus the rotation matrix. And then you've got this other object, which is a sort of curvature, which is the gradient of the rotation matrix. So it is something similar, not really the same, because here rotations can be whatever. This is a completely free gradient. It's a completely free degree of freedom. We had in the second gradient a sort of like curvature, but curvature was the second derivative of the displacement field. Here it is the derivative of the rotational of the rotation vector. They are similar, but not exactly the same. If you if you substitute these stress-strain relationships in the equation of motion, we obtain, I call them Navier, meaning that these equations of motion are equations of motion where the displacement field appear. Here, this I mean as a displacement field, both displacement, I mean generalized displacement field, that is just displacement field or rotation field. So you see that in this case, you've got a system of coupled equations. You see that in the balance, in the translation balance, also rotation appears. And also in the rotation balance, also translation appears. This is due to the coupling between strains as gamma, as a gradient of displacement, and gradient of rotation and curvatures. Okay. Yes.
In the previous slide, what should regain the Cauchy continuum when the rotational micro rotation is 0?
Not only micro rotation is 0, and also you've got to take the symmetric part of this, both things. Yes. It's not exactly the same. Okay. Yes, here just look at that, because the rotation balance can be written in different ways. Here I wrote it as the divergence of M. M is this matrix. But you can find in the literature also some cases when the rotational balance is written in this other way. So what is the difference? The difference is here M is a vector and M is a matrix or a second order tensor, and S is a first order tensor or a vector. You can find some papers where the rotation balance is written as the divergence of a third order tensor. The third order tensor is this object, which, as you see, contains the components of this matrix. This is obviously exactly the same. The only thing is that in this way, if you write them in this way, you can find the same equations repeated. So some equations you just will have to throw them out because they just repeat them. And this is something that really drove me mad, but I don't want you to suffer the same as I did. Therefore, I wrote down this slide. So, okay, now I would like to move on to the wave propagation in this kind of media, but before doing that, I would like to drink a glass of water and take a 5 minutes break. Okay, I'll see you shortly. Okay.
Understand between the two papers, to understand the relation between.
It's crazy. Yes, yes. Because just let me riprendi registrazione. Okay, so if you can all hear me and see the screen, I will restart the presentation. So we were here. Okay. Can you all see and hear me?
We are seeing I'm seeing a slide number 8, wave propagation in second grade media.
Sorry, can you repeat, because the audio is very, very low.
Sorry, sorry for my audio. Like, I'm seeing the 8th slide, which is titled as a wave propagation in second gradient media.
Yeah, but is it the large one?
Yeah, large one.
Okay, okay, nice, nice. So
for me, it's not the large one. It's like when you open the PowerPoint.
Okay,
And
so it's not the large one. No. No, look, guys, I will keep on doing exactly what I was doing before. Otherwise, it's too small.
Devi condividere il suo schermo.
Sì. Condividi schermo, yes. E se faccio schermo 2?
Infatti dovrebbe essere anche
No, ma...
Siete illuminato con schermo.
It is okay now.
Yes.
Okay, now it is okay. So you see it right now? You see the large one?
Yes.
Okay, nice. So, okay, now what should we do with Coursera Media? because a difference that we have in this case, yeah, the difference is also that I don't see the time, so I've got to do. Okay, here we are. Yes. Another difference right now is the fact that you do not only have to use to describe the wave character of displacement, but you've got to describe also the wave character of rotations. So when you want to understand which kind of harmonic progressive waves can propagate in a Coursera continuum, you have to substitute both of these two tentative solutions into the equilibrium equations. So you've got a displacement which has a given amplitude, which I called bold A. This is a vector because it's got 3 components, and a rotation which is bold B, which indicates the amplitude of the 3 rotations times the same propagating part. Propagating part, which again describe a plane wavefront propagating in space according to the direction bold N. Bold N, remember that the K vector is K modulus times N. Substitute these ones in the equilibrium equations, and you obtain a set, this set of coupled system of equations that tells you under which conditions harmonic progressive waves can propagate in a Coursera medium. Then, if you pick up your pen and start operating, trying to understand whether there is a spectral decomposition of the acoustic tensor, which you can abstract from here, you find that actually there is a spectral decomposition. So again, you find that these ones, you see that this part is the part of eigenvectors that span the normal to the wavefront. And this other part is orthogonal to the normal of the wavefront. Is a plane orthogonal to the normal of the direction of propagation. Therefore, again, we've got a spectral theorem, which ensures that these two terms describe longitudinal waves. But what are these longitudinal waves like? Because one is easy. You see, this has a velocity which is exactly the same as we found for the Cauchy continuum. And it is interesting because this one has got B equals 0, meaning that there are no rotations, there are only translations. So this is a pure longitudinal pressure wave, non-dispersive. Very easy. The second one, which is this one, instead is, first of all, dispersive. You see, dependence of speed on frequency. And moreover, has A equal to 0, because you see, this is 0. So the only part which is different from 0 must be B. But B, remember, is the amplitude of the rotation. So you've got a wave which has only one rotation. What is it? A torsion wave. So you can have, and the torsion occurs around the axis, which is normal to the wavefront. Okay, two waves, normal displacement, and torsion, rotational. And the second set of waves is a bit more complicated because their speed are determined from the roots of this other part, which is this part of the spectral of the acoustic tensor. Oops, what did I do? Can you still see it?
No,
Hey,
the
guys?
share screen stopped.
Oh, okay. Is it okay?
And we don't succeed.
Yes, it's visible now.
Sorry?
For us, it doesn't change either.
Oh, yeah, okay, for us, but it's, yeah, but for them, yeah, okay, yeah. Puntatore laser, okay. So, yes, I was saying this other part of the waves. Okay, you've got these two vectors, which define a plane which is orthogonal to n and to a. And this plane contains the components of the 4 eigenvectors that, in that case, for that part of the acoustic tensor, are mixed waves, meaning that they are displacement rotational wave modes. To give you an idea of what are these kinds of waves, because they can be both shear and bending. Think of a Timoshenko beam. A Timoshenko beam is described both by the displacement about the normal to the axis and a rotation. This rotation of the Timoshenko beam, different from the Euler-Bernoulli, is not the derivative of the displacement field. This is just a different coordinate. So if you can imagine a wave which propagates along the axis of this Timoshenko beam, you can have both displacement and rotations. And these two vectors are contained into a plane which is orthogonal to the direction of wave propagation. You've got a wave which propagates along the axis, displacements that are orthogonal to the axis, and rotations that are about an axis which is orthogonal to both the axis and the displacement. And this is actually the decomposition that this thing is telling you. Obviously, I told it in simpler words with the Timoshenko beam. This is three-dimensional, more complicated. In the case of high frequencies and large wave numbers, the acoustic tensor assumes an even simpler form, because there are some terms, in particular those ones, that one, and so on, which go to 0. Oh no, again. What did I do? I'm just tired, last half an hour probably. Yes, because I hit this one. Okay. No, got to use the keyboard here, not use the mouse. Okay. very delicate. Where is the? Yes, maybe like that. Yes. Okay. So you see, this decomposition is easy. It is understandable. This one is a little bit more complicated, but from this one you derive longitudinal and torsion. While these other two waves are mixed waves that involve both shear and bending. Now, representation of the dispersion diagrams for Timoshenko beams. Be patient, because in minutes I will show you a very nice application of all this stuff and how it can actually be used to describe real phenomena, real things that we can see in experiments. Why it is why it is useful and important to suffer so much for so many hours. So be patient, because applications are coming. So dispersion relationships, what are they like? I represented here just the real part of the wave number as a function of frequency. So you see you've got longitudinal wave, the red one, non-dispersive. Okay, we knew that. We've got this other shear rotational wave, this one, non-dispersive. It is one of the roots of this determinant. Two other waves, one torsional, we saw that before, it is this one. This. Done, dispersive. Dispersive and cut off. You don't see that before a given frequency. Nothing like that can be seen. This other one, shear rotational, second part, the right part of the acoustic tensor, the one so complicated, dispersive. Dispersive plus with a cutoff. Speeds, you've got to take the ratio. Longitudinal wave, okay, horizontal line, no point, nothing too scary. Shear rotational, well, a bit dispersive, it is this one. It seems to be a line, but it's not exactly a straight line. This one's infinite phase velocity, what does that mean? You can't see them, they do not propagate. Now, let's go to a model. This was done by Rui Ai, who was a master student of mine who graduated in May in mechanical engineering, and she developed a plane model of a Coursera continuum. Just to make it easy, I just wanted to understand what was going on. And in the plane model, you just have two displacements and how many rotations? One, about the plane orthogonal. So this is the definition of the various components, balance, strain, curvature tensor, and this is the model we did. Why we did that? Because we had some experiments that are ongoing at the laboratory in Marseille, in France, where they are placing sound in this part, in this blue part. Then there is a layer, a Coursera layer, sorry, Coursera, a layer, let's say a layer of XPS. XPS is an insulating, sound insulating material. So you've got something that propagates in air, it hits the plate, and with a microphone, the sound which is transmitted to this lower part is measured, because we want to be able to understand which is the correct model of this layer of XPS. You know that XPS is made of round particles all pressed together. It's something like polystyrene, things like that. Okay. So on the right, we've got a model. You see the sound wave which propagate. You see two sound waves because one is reflected by the upper part. You see, it's launched by the loudspeaker and it hits the upper part. But we are just interested in that one. You see this wave. And on the left, this object is without XPS. This left object is with XPS. You see what happens? One thing you can see is that obviously that the amplitude of this displacement, this is, these are not displacement, this is pressure. But pressure in air is just the sum of the derivatives of displacements according to the three direction, in this case, two directions multiplied by a constant. Sound pressure is just something like that. You see that the amplitudes are much smaller in the left case. Then, what did we do? We placed a Coursera model here, plain two-dimensional Coursera model. Why we did that? Because look at those results. These are experimental results. And you see the cutoff frequency. There is some frequency which, this is the Fourier transform. Let me check, amplitude. Sorry, this is the transmission coefficient. What is the transmission coefficient? The transmission coefficient is the ratio between the spectrum of the transmitted sound divided by the spectrum of the sound in the same point without the layer. This is the reason why we modeled these two cases. One is with the layer, the right one is without the layer. And this operation serves for you to calculate the transmission coefficient. So look at this result. This is an experimental result. In blue, you see the transmission calculated, as I said, meaning ratio between transmission and sound pressure at the same time if there were not the layer. And you see that this part is actually something that hints at the fact that sound just do not propagate in that frequency range. Why? Because the red one is the incident spectrum. The red one is the spectrum of the sound which was launched in the air. So it's something which is kind of broadband. It's something broadband that here, okay, here it dies out, but why doesn't it propagate in that frequency range? Because we think that this is because of the presence of a cutoff frequency. In fact, if you do a model of a Coursera solid with some properties that they do have, some mechanical constants that they do have in this laboratory that we were given, you find a cutoff frequency of around 6,000 hertz, which is more or less here. Now, probably it's a bit higher, but it's something that it's meaningful. And here you see our numerical results. they look pretty similar. You see the blue one? The blue one is very similar to this other one. So it is probably actually meaningful to do all that work and actually model the layer with a Coursera continuum, because it can respond very well, it can explain very well some phenomena which are observed in experiments. Obviously, we noticed that the transmission coefficient depends on the thickness of the layer, but this is obvious, as every one of you can know from practice, practical experience. And yes, the last comment might be that this is the pressure, the time history of the pressure. Let me check. Yes, this is without the solid layer, and this is with the solid layer of XPS. The amplitudes, as you see, are much, much smaller in the upper diagram. Okay. Yes.
Was there a microphone on the other side? The reflected wave?
Yes, there was a microphone here.
On the other side.
Mm-hmm. Yeah, sure. There was a loudspeaker and microphone, and the microphone also here.
So the microphone in the space of the loudspeaker checked out the reflected wave of the non-transmitted frequency.
Yes, but I have not analyzed that result. Also because I guess there are interaction with the chamber. I'm not sure about that. Yes, but anyway, there is a reflected wave. Yes. Yeah. Mm-hmm.
That would be the proof, the non-transmission.
Also, yes.
Sorry, the reason that the idea of using construct model was seeing that cutoff frequency?
Yes. In fact, these colleagues, you can see, you can read this paper, which was published in 2021 in the Journal of Sound and Vibration, and they started their work with a model, but they did not model wave propagation in air. They used some simplified Coursera model. So we kind of interacted for other reasons, and we started this collaboration because, I mean, we knew each other from papers and because we were acquainted in this area of study. So we decided to try using this approach, which is still ongoing. Unfortunately, I didn't have much time to work on it, but the idea is that, I mean, my master student did a lot because she set a lot of models, but there is still some work to do. Okay, and this is the end of, let's say, more theoretical part. I have collected here for this last 20 minutes a series of other applications. These are not pretty, there is a bit of, they are not perfectly ordered, but just wanted to mention some applications that all this research and all these theoretical models can have. This is an old part. I have not revised, and I'm not presenting it. This is something which is presented in the book by Doyle. It's a way that it's an approach to the modeling of the wave propagation in systems of rods and and beams. And I just wanted to mention 3 recent applications on which I am working. One is the propagation in pre-stressed media. The propagation in pre-stressed media is described by the theory of acoustoelasticity, and this is a theory which can be deployed at different levels of approximation. The classical theory of acoustoelasticity is just a theory. Here is one of the motivation why we study, I guess, to exit, because sorry, just a minute. Yeah, I know. This is one of the reasons why studying identifying stress is interesting, is important, and this is why kind of 10 years ago I started studying pre-stressed wave propagation in pre-stressed media, because I was saying at UCSD, in University of California, San Diego, which is in California, as the name says. And in California, they have a lot of this kind of problem, because there is a huge temperature excursion between night and days. So rail instabilities are really frequent, and they often cause spillover. They can cause a spillover or of pollutants in the environment, besides also the loss of goods that are being transported. So there is an interest in having some instruments to monitor the pre-stress. And one idea was to apply the theory of acoustoelasticity. The theory of acoustoelasticity is a theory which describes in its linear version. Are you still seeing my screen online?
Yes.
So it's a theory which accounts for non-linearities in the material, non-linear deformations, strength, components of strength, and also it accounts for the fact that equilibrium takes place in a deformed configuration. And with this theory, in the past, many researchers were able to describe the change in wave speed due to the initial pre-stress and pre-strain. You see, for instance, these curves that represent the change in phase velocity and in group velocity in a plate which is subjected to an initial state of pre-stress and pre-strain. Now, the point is that this change is kind of not very large, and therefore, at the moment, there is an interest also in some non-linear phenomena, which are described by non-linear theories, so higher order approximation of this theory. There is a student of mine who is Meng Wang, who graduated in mechanical engineering last year. I guess maybe he's online right now, and he's also a PhD student at the moment who has worked that subject. One of the things that are thought to be of interest to monitor the pre-stress and pre-strain is the arising of higher order harmonics. This is the case of a plate excited by a frequency, which is this one. So you see that due to the nonlinearity, it reacts, it responds to that frequency, which is the frequency of excitation, together with other higher order frequencies. In particular, here we have tested some conditions that are called internal resonances, which are described, I guess, in some slide here. Yes, this is called internal resonance. Because you see that these couples of waves, we have a couple of dispersion curves where motion can exist, can be sustained by the structure at exactly the multiple of the frequency. This does not usually happen, and in particular when there is when these internal resonance conditions are satisfied, the higher harmonics should be more strong than when these internal resonance conditions are not satisfied. So this is one of the applications. Then another applications which I guess one of you students asked me something about it. Yes, no, 2 days ago, is defects and inclusion image reconstruction using ultrasonic transducers arrays. An array of transducers is basically a set of a given number of transducers that can be, for instance, piezoelectric sensors and emitters that are generally placed on a surface, on a side of a plate. Generally, these ultrasonic transducers are placed like that because the plates are not necessarily all accessible. Therefore, a placement over an edge is preferred with respect to other arrangements. And this is an example, a comparison of what is done with the ultrasound you are done in your body when you have to be diagnosed some illness. For instance, this is the image of a cyst which is obtained by a manipulator, which is an array of ultrasonic transducers that the doctor uses on your body to detect an image, and the image of a hole in a plate made with exactly the same, applying exactly the same principles. The plate, there are additional difficulties with respect to tissues, because tissues do attenuate a lot the signal, so you don't see reflections from the boundaries, while in a plate reflections make often the definition of an image more complex. This is how things work. Basically, different images obtained by transmission and reflection using the different transmitters as emitters are superimposed until a clear image of the defect is reconstructed. Different techniques, imaging techniques can be used. One very popular and delay and sum. The delay and sum works like that. Basically, one picks up a list of time histories recorded by all this array of transducers, and for each point of the plate, this XF and YF are the coordinates of what is called focus, which is just a point on a plate. They pick up the amplitude of the time history at the precise time, which is calculated like that, which is in practice the sum of the distance which is traveled by a wave launched by a given transducer, from the given transducer to the focus, and from the focus to all the other transducers. So you pick up these amplitudes for all the points in the plate, and you reconstruct an image. You see, you launch a wave. This is reflected by the defect. You pick up the list of the time histories, and this is what comes up. This is the whole. This is the image obtained with the delay and sum technique. Obviously, there are many problems like the presence of the lobes and many other things, so that some techniques were formulated to focus the image. And we also contributed to that with obtaining these very nice images that are obtained by what is called compounding. That means that we have separated the contribution of the different waves that can propagate in a plate. For instance, in this case, we separated the contribution from the shear wave and from the pressure wave, and moreover, we applied some filters that are based on the physics of waves, meaning on the shape of the waves. That means that we projected the two components of the waves to pick up exactly the part which contributed to the response recorded by the transducers. Last applications is being developed by one of my PhD students who is going to graduate this year. Her name is Shayeste Naginajad, and she's working on the reconstruction using computed tomography. Computed tomography is a technique which derives from the Greek tomos, which means slice, which is based on illuminating an object and recording the projection over a set of sensor. This is do you know when you, I don't know, maybe some of you have done a tomography to your body. Again, you are put into a sort of pipe, and you can hear a machine going around your body, and it does that in slices in space interval for all the length of your body. And this is a technique which, based on the projections, enables to reconstruct the inside of the body without actually making cuts. And this is based on the use of an algorithm which is called radon transform. Radon transform, there are theorems that guarantee the relationship between the image and the projection and its projections. It's called Fourier slice theorem. So what did we do? We expanded. The point is that this theorem is applied in 2 dimensions. The same Radon, who was a mathematician, the guy who formulated these theorems and these who had the idea of this transport. This guy also suggested that this technique could be applied to higher dimensions. At the moment, most of the algorithms apply it to 2 dimensions and make slice. We had the idea of applying it to 2D projections instead of slices to just obtain a 3-dimensional image. And we did that. We expanded the theorem to 3 dimensions, and we applied it to the image of the light emission of plasma. This is an experiment which is undergoing at Enea, and this is helium or helium plasma generally, or hydrogen plasma. Plasma is a state of a matter which is which establishes in this sort of chamber when an electromagnetic field is generated by 2 electrodes, which are on the top, on the bottom of this sort of tokamak, let's call it, but it's transparent. An actual tokamak, it's iron. Here you can see through it. And the idea was to recreate the same spatial distribution of plasma that establishes in a tokamak in this other chamber. And this is still, obviously, as I said, an ongoing experiment, but by applying these algorithms I have described to you before, we were able to reconstruct these images of the light emission, and also we were able to demonstrate that plasma actually rotates within this environment, and yes, that's the end of the story. That's the end of the stories, and our friends at Enea say that this is the first time we people managed to observe that plasma is actually rotating. And that's it. I thank you all for coming. Thank you for listening. And if you have questions, I'm here to answer. If you have questions in the future, I will try to answer if I can. If I cannot, you will answer. I can help you, but and yes, that's it. Thank you. Question?
Thank you.
Questions from the audience? Yes.
I don't know if this was this presentation, the 25th slide of 71. I don't know, the parts about the governing equations of Corso.
Okay, yes. Yes, these are not numbered because in the end...
trying to understand the logic.
No, there is no logic. It's just a mess. I mean, the first 2 lectures were very ordered because I had more time. This one was a bit more. Next year.
Sorry.
Next year.
And in the conservative equation.
Yes.
is it exactly?
The J? This is a very nice question. Okay, the J, in fact, I found a value for this model, and I pick it up from this paper. But in general, this paper, this one here, in general, this is called microinertia. What is it? I don't know. Because if it is a particle of, let's say, spheres, I mean, if the Costello continuum is an ensemble of spheres, okay, you calculate the inertia of the sphere, which makes sense. So I'd say that maybe we could call it inertia of the average particle per unit volume. If I had to do a model, inertia of the average particle per unit volume.
Average particle.
Of the average size particle.
We need the microstructure, the material.
Look, you do like that. But I did that with a disk, you do that with a sphere. Okay, this one here. You calculate this one here. This one here. You can, oh, sorry. This one here. For the average size particle, and you divide it by the number of particles that a unit volume, can contain. So average, I will try like that. Average inertia.
How we can calculate it, for example, if we have an RV material that we want to find the equivalent Passerelle model of it. If it's
An RV has got particles, so you can calculate rotational inertia of that ensemble. You can do it. You calculate this object for the volume, or if it is a plane, you apply exactly the same formula.
But is for a three-dimensional thing, which is not enough.
For a three-dimensional, yes, it should be a diagonal tensor. Let me think. Yes, should be a diagonal tensor. Yeah, because you got the rotational about 3 axes, so it's 3 components. Yes.
But you know that theory is for a continuum space,
Mm-hmm.
for a continuum body.
Mm-hmm.
I mean, when you write the Costelloids, you do not really consider, for example, that there are particles. But in a continuum equation, you have something that, because I checked, for example, the book of Eringen for micropolar theory, nowhere is any description of what is the physical meaning or what is
yes, look, but I think that this is you. Let me